Now you should be completely aware of how we derived the result that net force multiplied by delta S has to equal the change in 1/2 mv squared, and that we call F net delta S the work done by the net force, and the change, well, 1/2 mv squared is kinetic energy, so this will be the change in kinetic energy. Now, you should also know that this came about because if we substitute A equals F over m into the fourth equation of uniformly accelerated motion. And I'll mention this has only been shown for a case of uniformly accelerated motion, but it's a general principle. We haven't done the integration, we haven't seen the integration that leads to this, to the validity of this in all cases, but it is valid in all cases. Okay, so having done that derivation, and that was done a couple of weeks ago, but you've seen documents that you were asked to work through that reinforce this in many ways. So you should have seen this recently. You should be aware that then that the change in kinetic energy is the change in 1/2 mv squared, obviously, and that's going to equal 1/2 mvf squared minus 1/2 mv naught squared. And of course, this is the way it originally appears when you rearrange that equation after having substituted F over m for A. And then we define this to be final kinetic energy, initial kinetic energy, and of course kinetic energy in general is 1/2 mv squared. Okay, that wasn't handed down on a stone tablet. That's just a series of actual shortcuts that we end up being able to take if we make that substitution. A equals F over m into the fourth equation of motion. Or do the corresponding set of integrations to establish this principle in every case. Well, I mentioned all this now, but it came up in the solution of the problem because people didn't seem to understand that 1/2 mv squared would be 1/2 mvf squared minus 1/2 mv naught squared. And also, this holds only if your mass happens to remain constant, which is usually the case in most of the situations we're going to encounter. If it doesn't, you got to use some calculus, and you got to be careful. Okay, well, if work 400 joules is done by a net force on 5 kilograms with initial velocity 10 meters per second, then what's the final velocity? And you're asked to solve this without any recourse to the equations of motion. Well, and you don't have enough information actually to use the equations of motion in this situation. So what do we know? We know the work done by the net force, because this is a work done by the net force. We'll call that delta W net. And you know the mass, and you know the initial velocity. Now again, when we did this in class, they said, okay, you know this stuff, and you know this. Now what can you do? Nobody seemed to want to make the connection that, well, if you know mass and initial velocity, you at least know the initial kinetic energy, KE0, or the 1/2 mv naught squared. And, didn't seem to have a lot of awareness of how all this was related. So, anyway, m and v naught do allow us to determine the initial kinetic energy. And then, since we know delta W net, and the change in kinetic energy is the final minus the initial, we can calculate the final kinetic energy. And then having that, the final kinetic energy being 1/2 mvf squared, knowing m, we can solve for vf, get our final velocity. Now, the calculation scheme is very simple. Right there it is. The details are equally simple. Initial kinetic energy is 1/2 5 kilograms times your initial 10 meter per second velocity squared. And that ends up at 250 kilogram meter squared per second squared, or 250 joules. Okay, so what's going to be the final kinetic energy? Well, the final kinetic energy, since the work done by the net force is a change in kinetic energy, which is the final minus the initial kinetic energy. It turns out that the final kinetic energy is easily obtained by adding the initial kinetic energy to both sides and getting, well, the final kinetic energy is going to be the work done by the net force plus the initial kinetic energy. And the work done by the net force is 400 joules. The initial kinetic energy is 250 joules. We add these, we get 650 joules. So the net force does 650 joules. The final kinetic energy is 650 joules, which means then that we can easily find the final velocity, because then 1/2 mvf squared equals 650 joules, and we can solve this for the final velocity. There's always a tendency, when possible, when people are working work energy problems for the first time, to revert to equations of motion, the analysis of uniformly accelerated motion. There are two problems with that. One is you usually don't have the information you need to get into those details. The second is that the analysis of uniformly accelerated motion is completely irrelevant to any situation where the motion is not uniformly accelerated. Now, we only derive this for the case of uniformly accelerated motion, but as I've said, we haven't done the calculus of it. I want you to get a little more used to the idea of variable forces and the work done by variable forces, so it makes more sense to you before we do that. But you need to take my word for it, at least right now. Or if you don't want to take my word for it, go ahead and look up the proof of the work kinetic energy theorem and see for yourself. So the second problem is, or the second reason that you don't want to get in the habit of going back to uniformly accelerated motion, is that the motion isn't always uniformly accelerated. We can ask perfectly good questions about work energy relationships in situations where acceleration is not uniform. And there's a third idea, that this idea of work and energy and the relationship between work and energy, while unfamiliar at first, is really powerful. It simplifies our thinking immensely to have this tool at our disposal. So make sure that you approach this in the intended fashion. Don't go back to the equations of uniformly accelerated motion. Don't use them unless it's absolutely necessary to do so. I should say absolutely necessary and appropriate, because you don't want to use them if you don't know that the acceleration is uniform.